Good morning. So today we continue talking about secondary structure prediction. Again, there's no lecture on Thursday, neither on June 3rd, Tuesday, and then June 10th. I want to announce 2 courses, and I will repeat that at the end. We have 2 times 15 slots for 2 courses during the semester break. They are electable as modules IN 0014 and IN 2107. One is on Java script technology, and one is labeled patterns and anti-patterns, examples for better coding. Supervisor is Guy Yagdav, who will fly in from New York for giving these courses. The pre-meeting will be in June. Do you remember the date?
No, it's not settled yet.
I believe it's sort of towards the 17th, roughly, as far as I remember. And the courses will be held as a block at the end of September. Please register via email to Guy Yagdav. Recap on secondary structure prediction. So again, structure is determined by the sequence, by the amino acid sequence that interacts with the environment to form a unique 3-dimensional structure. We can identify similarities between proteins and identify, in fact, whether 2 proteins have similar structure just based on by sequence comparisons in the daylight zone, coined by Lothar. Sequence profile comparisons get deep down into the daylight zone, beginning into the twilight zone, and then at some point profile comparison take it on. Nobody really gets into the midnight zone. All of this allows us to model 3D structures through comparative modeling for about 1/3 of all the proteins. Comparative modeling simply is I take a sequence for which I don't know the structure, I run it against the database of experimentally known structures, identify at some level of similarity, a hit, and then I say it has the same 3D structure, and I begin to model a little bit of the detailed energetics around it. For instance, for loops. For the other 2/3, roughly speaking, we cannot predict 3D structure. I will talk later about contact predictions. We are not very far here. We can only actually predict 1D structure, secondary structure and solvent accessibility. Secondary structure formation is sort of stabilized by hydrogen bond formation, many of them. In the helix, bonding is between I and I+4. In a beta strand, it's across 2 strands, forming a sheet. I talked about the first generation methods, Chow, Fassman, and Gore, that actually predict sort of log odds for a single particular amino acid. So I show here 3 different valine residues, V's, at position 32, 36, 51. And the probability that this first generation of methods assigns is completely independent of where the V is. The probability is for the V to be, in this particular case here, in a beta strand. And therefore, for position I, it's the same as for position J for all I and J. Now, the second generation methods drop this assumption, and Gore 3 is a representative for those. They now compile odds for windows. What I mean here is I simply consider, in this particular case, a window of 3 means 3 on this side, 3 on that side. I predict secondary structure for the central, that's the I here. And I consider simply what is next to it. So now in this particular example, in the second generation method, the probability may be different for V32 and V51 to be in a beta strand. Simply because it sits in a different environment and the probability is compiled according to this environment. Local sequence environment is what environment means here. I told you that there are problems with secondary structure prediction methods as I've described them so far. One, they don't reach 100% accuracy. Argument there was 65 is the top we can do because more is not determined on the local window. In the slide before, I showed you a window of length, so I had a W of 3, a window of 2 times 3 plus 1, so 7 residues. Similarly, beta strand prediction is very poor at levels slightly above random, only because the strand formation is non-local in sequence, and there are short segments predicted. I introduced to you the idea of neural networks or machine learning. Here in this particular case, this is a neural network where you have an input layer. For our case, those would be the amino acid sequence. An output, for our case, this would be, for instance, 3 secondary structure states and something in between hidden layer where you can blow up the hidden number. Those are part of your free parameters. The training curve is like this, the testing curve like that. There is a point beyond which there is somehow overtraining. Okay, let's get back to this issue and let's get back to the questions. This intelligent device of machine learning, can that actually solve any of these problems? I briefly commented on how you would implement a neural network. Here's a more detailed view. So what I show is 13 adjacent amino acids. So position I plus 1 and so forth. At the center position here you have a P, proline, and in fact the system is supposed to learn the secondary structure state of this proline in the center. In brackets you see the actual observed secondary structure. I told you that P in the first secondary structure prediction method by Sengerji was predicted to be a breaker of a helix. In this particular case, in fact the P is sitting in a beta strand adjacent to a helix though. Now whatever, so the central secondary structure state is going to be predicted. We have 3 outputs, HEL, helix strand other. Here's one way of coding this. Now this I said is 13 adjacent residues. So you slide this window through, you predict P, you slide by 1 and further on. But each one of these ellipsoids or ellipses here is in fact filled by 20 amino acids. And in fact we need 21 units. We need 21 units because we need a spacer. This is simply because when the central residue is the first, so when this I becomes 1, then in this particular case you have 6 residues for which you don't have a position. Non-amino acids, so it's before 6 positions in the neural network here before the beginning, if that would be the first residue, the P, right? And for that you have the spacer unit here, the 21st unit. There are other ways of doing it. Many aspects of the way you use machine learning are heuristics. You find a lot of heuristics in books. Mostly, this is not worth the paper that's well, today it's not written on paper anymore. That's not worth the internet time you spend on looking at the data or the time that you spend on it. Usually the point really is that every machine learning task fits to your problem and you have to spend some time making it work. Again, that has to do with many things. For instance, this aspect of how is the best coding. You could imagine to code them in many other ways. And may get back to that later. So the major question is, the first major question is this going to get closer to 100%? I told you that the second generation method sort of reached 60 something percent. What do you believe? Is this going to get better? Machine learning as opposed to dumb statistics? And the numbers that I showed you now, will show you, are old, but not quite outdated. We get a little bit higher today, but not much. Are we going to get up? Yes, we should. So the number that I show you is something into which I spent 2 years of my time. And I very much felt the same way as you. We should get up. I mean, come on, why should I waste 2 years of my time, right? 62%. Pretty, well, I could show at the time this was sort of borderline of significantly improved, but clearly not what I had hoped when I told myself it should get up. Now, in some sense, the idea here has been the developer, in this particular case I, had just hoped using a new device would help me. Just throw enough data at it without thinking, so to speak, and see that it works. Now that didn't work. But let's just look at an example of something else. When I look at the dynamics of the system, so what I show here is training time. The way a neural network is trained is that you present known examples one at a time, and you optimize the connections. such that it learns these known examples. This unit is here, 20,000, 1 is 20,000 steps. I had roughly 20,000 examples, so I clocked it such that 1 unit here is 20,000 iterations. This is the performance on the training. Other is green, blue is strand, red is helix. And what you see immediately is that in the first step, other and helix are already learned. Green and red reaches levels that are very similar to what it reaches many epochs later, right? So 20,000 towards 200,000 training steps, green and red is very similar. While you see that what is happening is that the system gets much better at learning strand. That's not quite what you want. You clearly would like to be somehow have a similar accuracy in all 3 states. Now when I look at whatever it learned after some time, and I ask what fraction of the residues that are correctly predicted are in one of these 3 states, helix red, beta strand blue, and other and white here, you see that indeed this ratio here also clearly other is predicted the best, second best helix, and the poorest is beta strand. Now, what you see in the database is this one. Anybody jumps at something?
There's definitely more data for others and helix. So, of course, the training data is like, it has more examples. So, of course, the accuracy is better.
Of course is a big word. Be careful jumping too quickly into logic. But it's remarkable how similar these pie charts are. So your assumption has been, and that's what you argued and that's what you meant by of course, is what I train is what I get. Not necessarily the case. So it could be that one of those states is overrepresented but is impossible to learn because of whatever reason. So that's why I'm saying be careful jumping too quickly. Clearly, what I wanted is something more like this. I'd like to have a method that sort of evens out my performance so that predicts equally well between the 3 states. How can I force the system to do that? Or how could I try to force the system to do that? That is my database situation.
I mean, instead of training 3 separate threads, you could try to connect them all to the training set. So like if you have an error, you can try to have an overall error instead of like separate errors.
But this is an overall error. So my error function simply is I have 3 output units, and I sum over those that make mistakes. And there are different ways in which, in fact, I do that. I tried many different things. Ultimately, this really is a sum over the difference of the 2 vectors, which in fact comes very close to what you say, right? If I understood correctly what you meant, and this is exactly what you want. So that is already what I'm doing. Any other idea? Hit it harder. Does anything come to your mind where that sort of is much more aggressive and may strike you as much dumber or much more the kind of wrong thing to do? Anybody? So again, underneath, if I follow your logic, then the problem is the distribution that I see in the database. What can I do about that? I cannot create new data, yeah?
You can like cut the data.
I can cut the data. And that in fact is exactly what I did. So rather than in fact sort of doing an error correction every single step, now I do 3 steps. 1 of strand, 1 of other, 1 of beta strand, 1 of helix. This implies, this is a simple formula, what it implies is that you actually oversample. Or oversample is one word of putting it. Another word of putting it, you sample equally. Since strand is less in the database, effectively you oversample strand. That's all that this formula implies. Again, that's what I call unbalanced, the real data composition, and that's the balanced. So you see, again, your logic appears to be entirely confirmed here. You see, you artificially change the database, and you get exactly what you want. Namely, you get an equal distribution. There's one downside to that story. Now, the overall accuracy drops. This is simply because now I have forced the system to predict strands as accurately as everything else, because there are fewer strands, however, in the database. That means my overall accuracy is dropped. Overall, for the Q3, that simply measures how many residues are correctly predicted in either of 3 states. Overall, this one was better. But clearly, this has sort of something that is more of a local effect. So the statement 1 here is that neural networks do better if you understand your problem. This one was relatively easy. So what I showed you first the training dynamics. That's the part that made me stumble. I could have looked at the database before, but the trouble is that in fact your logic assumption here, the distribution of the database is what you get, is too often not right. So that's why somehow this didn't hit me. Too many people have seen that in too many scenarios. But when I saw that during the training there was really one state that was learned last, that sort of hit me. But it was coincidence. Now, here's another aspect that is important in this story. Remember I told you the argument why beta strand was predicted at levels just about random was that this strand formation is non-local. And that's a biochemical argument or biophysical argument that is absolutely impeccable. It's totally true. But it was not right. You find tons of papers still today that claim that this is true, and that is in fact still the case because methods are now mostly optimized to do the Q3 overstate right. So most methods are not balanced. Most methods out there in fact do the beta strand not as well as they could, simply because the overall number is not as high, and that is let's call it a different choice of the developer. But strictly speaking, whatever you see is not necessary. So you observe strand is less accurate. You have a reason why you can explain that. Just be careful. It's a correlation. So the conclusion here is not all sound explanations are right. Let me see whether I can switch the talk. Oh no, I threw it away. Okay. Now, the other problem, if you remember, was, so again, the first problem I have not addressed. The second problem I have addressed. So I'm a little bit closer to 100%, but by no means in a significant way. But I can do much better for beta strands. What about the last problem? The last problem was that the method predicts 2 short segments. And does the machine learning device do better? Here's the answer. The neural network predicts on average strands that are 3 residues long, helices that are 4 residues long. That's what you observe. So this is also, again, too short. How come? What's the problem here? Can anybody suspect a reason? Throw an idea at me? Why could that happen? Again, the statistics do the same thing. It's not specific to a machine learning device. In fact, this is actually for the machine learning device slightly, significantly, in this particular case, better than for statistics, but still not good. How can that happen? It goes back, sorry, it goes back to the way the dynamics is done. So the connections, junctions in the neural network are optimized by going downhill in the error function. So that's essentially what you say. That's the error at a particular time step t. You change the connections j such that the error decreases. So you go downhill, downhill. That's the minus That epsilon simply says don't jump too far. And that term here allows you to have a little bit of an uphill move to jump over local minima. That's all about this formula. But in principle, it's a trivial formula, right? Go downhill. Now, you could, again, machine learning in textbooks says do a sum over all your samples and determine the way you go down according to that sum. In practice, that doesn't work. You never have, so previously there was somebody here in the room who was very worried about CPU time for that thing. That is just completely impossible in terms of CPU time. So instead what you do is you have tiny jumps, and tiny jumps you create, so partially by this epsilon, but partially by presenting these samples one at a time. As I already told you, you do one beta strand, one alpha helix, one other, and then determine downhill. Next, downhill. Now, when you choose the samples, you cannot take residue 1, 2, 3, 4, and so forth. Instead, what you have to do is you have to randomly, you take your entire data set, training set, and you randomly pick the points. Otherwise, you get local correlations. And that's not good. On the other hand, local correlations in terms of I and I plus 4, they are good. I want to understand the biochemistry. If that residue is in a helix, that residue is in a helix, then the one in between will be in helix 2. Most likely, at least. There could be that one breaks. No, there is no helix broken by one single residue. So this example that I showed is a clear case. If the flanking residues on a helix, the one in the middle is true, just because the way the helix looks. But the same is actually true for a beta strand. If some device predicts that this residue is not in a beta strand, this one here or that one, then that cannot be the case if the others are. So the system has to somehow learn correlations between I and I plus 1. How can we get that into the system? So the trivial solution that resembles what I did before, that I oversample the data. So the trivial solution could be I train I and I plus 1 and I plus 2. That's dangerous, because then you make the system learn something that will not be true in general. So then the system will learn a particular valine always following alanine. So that goes in the wrong direction of space. You want to learn that correlation without really doing I and I plus 1 in 2 different time steps. How can you do that? There are 2 solutions that I can think about. Maybe you can think about a third one. Or one of those 2. So again, what I want to put into my system is somehow local information. If I and I plus 2 are in a beta strand, then I plus 1 is as well. How can I force the machine learning device, how can I force that information, that knowledge upon the machine learning device? No idea? Yeah?
You can either try to hard-code it maybe into the...
Yeah, but how would you do that? So for those of you, if you haven't heard it, hard-code that concept into the machine learning device. How could you do that?
Probably if you like use a firm data set which shows the correlation and try to...
Yes, but now you're getting into what I tried, you don't go that path, which is in fact, you train at one particular time step with I and I plus 1 and I plus 2. And this is, so I can tell you it doesn't work, okay? I can argue why it didn't work, but it absolutely doesn't work. It goes very wrong. Very wrong is defined as the device not only does not predict longer segments, but it reaches a very, very poor performance. Oh, sorry, let me go back. When I did that, I tried that out first, and I failed. Maybe that today things would look different, but I have no reason to assume that. So I cannot, in that sense, hard-code it. There may be a way in which I can hard-code it, but in fact there are 2 ways in which I can, the words that you used, hard-code, fit to what I'm going to show you. I'm going to show you both solutions. first one and later in the talk the other. But I'd like somebody to come up with an idea that okay. One solution is this one here. Essentially what I do here is I have two layers of neural networks. So this is, you may remember that initially I showed you a neural network that in the central position had a proline that was in a beta strand. So this is that one, 13 adjacent residues predicting 3 secondary structure states. Now I put the output of what that system predicts as an input to another one, but in this particular case has now 3 adjacent residues. In fact, it will also have 13. I just couldn't draw them here. I didn't have enough space. And again, now the input to them is the second level here, is the prediction of the first level. Again, I need a spacer because this thing, at some point, the proline will be, or the first residue of the protein will be there, and then I have to have the -6 or whatever the number of the window is, the -W as a spacer. That's why there are in fact 4 input units per residue. The output is the same, the input is the same, the training is the same, except that the input now is the prediction of the first. That system can directly learn that if that one here is in a beta strand, okay, better example, that one is a beta strand, that this here would have to be in a beta strand too, or has a certain probability depending on that residue also being a beta strand. This is what we get. So the second level here predicts, you may argue still too short, so the helix is a little bit too short, but this is way better. And it's a very, very simple trick. It's a trick that is done through the same device in machine learning. I haven't done anything special. This is just a totally trivial trick. I've seen the problem, and I simply used my device to address exactly that problem in the language of the device. Right? So it's simple. There's nothing clever in here. There's no big math. The other solution that I'll show you later involves something much more complex. In this particular case, it's a hack that doesn't even change the algorithm. The second level here is trained exactly the same way the first level is trained. Okay? There is a little bit of an issue here. You could, remember we had this split into 3 different data sets. The training, cross-training, and testing. So you might argue that the kind of split, bless you, for the first set will be a different one than for the second set. So you could actually sort of split it further, and there's something to be said about that. When I did it, the data set was too small to do this. Maybe today that would be possible. So I simply used the same split. I used everything the same. So this was trained on the same set as this one. It was cross-trained on the same set. It was optimized on this one. The connections were optimized here. The number of hidden units optimized here, and both tested on the same set. Now this shows you simply the overall segment length distribution between the method was called PhD that I showed, blue, red DSSP, so the observed, and you see that there is a remarkable fit with some differences. What I showed you here was in fact not sort of the first time this idea was invented. The first time this idea was invented was by 2 machine learning experts, Chan and Chinovsky. Terry Chinovsky, in fact, had applied neural networks to the problem of secondary structure prediction first, and they had used the second level, but they had applied it to improve the overall performance. Had not realized that they could use it for length, and it did not help at all for the overall performance. In fact, the accuracy that came out of the second level was identical to the one that came out of the first level. So the machine learners had done something that made sense, but it had not made sense for their problem, or for what they wanted to do. They had not, and they had completely overlooked that it actually did something totally different. Okay, now how can we improve from here? Okay, I should have had a question mark in here. I said we can reach 62%. We solve some problems. We have longer segments, that's good. We're better on beta strands, that's good. But we're still very much below 100%. We just improved a little bit, 60 something. What can we do? Now that's sort of the final step. I showed you 2 examples how the machine learning device, cleverly used, could solve problems that nobody else could solve before. How can we attack the third one? What can we do in order to increase performance? Again, the argument had been performance cannot be higher because signal structure formation is coined locally. But every other argument that people had made for a long time was wrong. So let's just be agnostic here and don't believe in that one either. Let's assume we can improve. How can we? And indeed we can. Any idea? So there are 2 simple ways that in fact don't work. The first one, I haven't even put on the slide. The first one is to blow up the window. So I showed you a window of 13 consecutive residues. Let's not take 13 if it is a problem of local. Let's take 50. And that doesn't work. Why may that not work? Any idea? What could be the problem? Why doesn't blowing the input space or the input segment up help you?
Probably it means if you have more input, it means you have more features, and so you need more data, but you don't have more data.
Exactly. So that is explanation number 1, and it's a very important one. You're getting into a realm in which you just don't have enough input into the example, or enough data to fit your problem. That's problem number 1. Problem number 2, in fact, in those days I couldn't see, but when more data became available in the following decade, I could verify that in fact the problem also was that residues too far away from the central residue that I want to predict just are not informative. In 1 of 100, they are important. But in the other 99, they give you completely the wrong signal, no matter how much data you have. That makes it complicated. In this particular example, you need an explosion of the data by a factor of 100 or 2 orders of magnitude. And that we didn't have. So here's another idea. Blow up the output space. So I said that in fact I have 3 signal structure states, 3 output units. Instead, use sort of 9 units or an average output over, and there are some reports that this may sometimes help. Here's the second idea in which I sort of could approach this problem of short segments. And this is introduced as a concept by Burkhard and applied to this problem of signal structure prediction by Gianluca Polastri. And the idea simply is, now the input goes from here, so this is sort of inverted. I showed you the amino acids here, now it's here. And in this particular case, what the system does, it feeds back the previous training step. And that's what I earlier talked about. So Burkhard is the person who really worked out, and Paolo Frasconi, in fact, is behind this idea of training this network. It's way more complicated in terms of CPU, in terms of math, in terms of really understanding. This is absolutely no longer straightforward, but it's another way in which you can sort of solve the same problem of the short segments. But all of that does not really help you to increase the overall prediction accuracy. Overall, you still have something like 60+%. Somehow we have to get a way to get more data into the system. How can we get more data into the system? Again, cannot just make it longer. Any other idea how I could put more data into it? The answer is the data is in the evolution. And this figure I showed you before, I showed you before to talk about pairwise alignments and where they succeed and where they don't. I showed you before to define the daylight zone or the transition from daylight zone into twilight zone. Number of residues aligned, and that originally has been published by Chris and Ryan Schneider. Percentage sequence identity, such that everything above here, if naturally evolved, has a similar structure. 100 residues aligned, more than 33 are identical, the two proteins essentially have the same 3D structure. When I first showed you that slide, I also said that if you go into a lab, or if I go into the lab and change 5 residues, so once again, the protein or the nature can change 67. I change 5 in 100, most likely I will create something that will not fold into a unique 3-dimensional structure. So I will knock it out. That brings up the question, how come that nature can do 67 and I cannot even do 5? Well, one answer obviously is I'm a poor thing compared to nature. But the real statement underneath here is that nature realizes something that is extremely unlikely. And neutral mutation is very, very, very unlikely. Why do we observe it? Because that's the only thing that survives. So what you see is a track record of an unlikely situation. Changes that do not alter things are unlikely, yet that's the only thing we observe, everything else dies out. Okay? That's a remarkable reality. And that reality also implies that, in fact, which residue can be exchanged at what particular position is very informative about that particular structure. Okay? How can I learn about which residue can be exchanged at a particular position? Well, that one shows a multiple sequence alignment here, where completely conserved columns in purple. You see that some columns you can exchange and some you can't. Now, this is mapped upon 3D. It's not a stereo view, so 2 different sides of the molecule. You see that the first completely conserved column here is this residue. The last one is this residue. They are close in space. They're not close in sequence, so very far apart. Now imagine you picked out 5 consecutive residues here from this. Since the object evolves as a 3-dimensional object, everything that sort of is here is influenced by something that is here. That means that you may see changes in this one if something changes here. That means that if you cut out 5 consecutive residues and look at this profile here, you have some imprint of something that happens elsewhere in sequence. Somehow it's like, you know, you look at a raindrop and you see the world. That's the image. It's really true. It's in this tiny little thing. You see something else. You may not be able to understand it. You may not be able to get it out, but the information is there, or some of that information. If you think about it, it's sort of transferring one problem like this one into another problem by averaging out over different organisms. The way to apply that, to put that into the neural network, is simple. You use the same neural network as before. However, now, instead of just putting in that it runs the sequence here, in my example it still is the proline here in the middle. Instead of putting this proline in, I put the profile in. So I ask, how often do I see proline at that particular position? For the proline, it's in fact 100% conserved. So I would put the P in. Here, I would put D, V, V, E, so that would only be 20% for D, 40 for V, and 40 for E in this particular case. So mathematically, in terms of, instead of having a sparse coding where 1 unit is 1 and 20 units are 0, I now have a vector for every single amino acid position, for every single residue, that has other numbers in between. It can still be 1 and 20 zeros, or it can be almost everything in between. That's what you take from this profile. And then you do the same thing as before. In order to make that work then, what you do is you start with your sequence, you search against the database, you find through BLAST, you find hits, you refine the hits, you filter according to this curve that I showed you to decide what you believe has similar structure. So everything above you use to build this alignment. You put this alignment into that system. That system now again has 2 different levels. So the first level and the second level for the better segments. System was originally called PhD, as I already mentioned, and it uses in fact additional input units. There's another step. I said before that neural networks find one particular hyperplane in space to separate out the points. And different hyperplanes in this particular case here are the gray lines. Could be created by different starting points with your initial connections. Could be created by a different number of hidden units or different training procedure. There are different ways in which you can create different lines. If these lines, now if you average over these lines, what you will reduce is the white noise, the random mistake. That means that as long as the mistake you make in the end is somehow not systematic, but somehow white noise, then using several networks will help. A simple average over several. In fact, if you had enough CPU, the more you do, the better. So the group of Brunach at some later point, I should put that here, published an example where 1,000 networks improved the performance. But then we get into something where really this is academic because it takes too long and the improvement becomes too small. But for a couple, in this particular case, the run was done over 12 or 14 or something networks, or 13, and there it clearly was a good payoff between speed and improvement.
But how does it differ from the architecture? I mean, you only showed us one architecture right now, with the 3 layers, and then connect all 3. So if you use different neural networks, they all have different architectures, because otherwise it's
so the output was the same. In fact, what I did not put in here, in the strongest way in which you can create different networks is, so this is the first level here, and the first level you can train balanced and not balanced. Okay? Now the second level you can come in with a balanced and can train it balanced. So 2 times 2 you already have 4 different networks. Again, the architecture of each of those is in principle the same. They have the same first level, second level, 3 output layers, nothing has changed, but the training dynamics has changed a lot. And you already have 4 different ones. I can't remember how I got it to much more than 4. But according to that logic, I had another sort of rough differences, and that created something in the ballpark of above 11. The architecture is not changing. Even if it would, I'm not entirely sure what you mean by architecture. So architecture could be the number of hidden units. What I'm averaging over in the end is the classification, is the output. I'm not actually, so what I cannot absolutely not do, oh, I'm sorry. No, I understand your question. Sorry, it took a while. I can absolutely not average over the connections, because then I create a new artificial universe in some sense. Every network in its connections creates a hyperplane to separate out the points it has. Adding random numbers to these points completely changes that classification. The connections or the hyperplanes, this is a very complicated, so the input, we're talking about something in the ballpark of 1,000 input units. So with 20 input, with 20 hidden, so 20,000 dimensional space, highly complex. You will almost never get 2 similar classifications. So the idea that I put in the slide here, simple lines, they are close to each other, is a complete simplification. So the averaging is not done on the networks. You couldn't do that. It's done on the output. I'm sorry that I didn't understand that question before. And in fact, today, the one on the network is even a little bit more complicated. It uses also predictions of solvent accessibility. It has a 3rd layer. The 3rd layer uses the sequence again, the profile again, and the predictions from the other 2 layers. Then there is a jury in this particular case here over 20. And then you get something like this. So the observed one is very on top, the secondary structure here, and that in fact happens to be the same molecule for which I showed the alignment. That's Chow-Fussman, that's sort of 1st generation here. That's Gore, 2nd generation, Gore 3. And that's the method PhD. Let's look at the overall performance. So I said that Chow-Fussman, so single residue statistics, typically get you 50 to 55. So for this particular case, the prediction is above average. Here I said that typically gets you to 60%. This, again, is above average. This one here says 72. Okay, so if that would be the case, then clearly we would have done much better than the 60-something that I talked about before. That's the distribution of this early system. Per residue accuracy, so for each protein, how many of the residues are correctly predicted, or what fraction of the residues is correctly predicted to be in one of the 3 secondary structure states. That's the number of chains. Overall, you see that, the average is pretty close to the 72% that I showed. So the example that I showed before for this neural network using evolutionary information is in fact just about average. It's better for the first generation method, it's better for the second generation method, but just about average. I'm sorry. Now, there's a good news in this slide here. Some proteins I predict very, very well. There's bad news in this slide too. So some proteins I predict much less than random. So if you were an experimental biologist and all you cared for is this particular protein, one of these, I can't remember the acronyms, it's too long ago, but one of these is a cold shock protein, then you would be very disappointed and would better throw away this machine learning device and use a coin. The coin would do better than that. So the coin gets to 35 or 30, depending on how you sort of bias the coin by your states. Whatever you do, 30 is really a bad answer. Could you have seen that before? And the answer to that question is yes. I should have possibly spent another slide on this. Again, my output is HEL. I show you two different predictions. In one, the values of these output units are 0.5, 0.4, 0.1. In the other one, it's 0.8, 0.1, 0.1. In both cases, the final prediction is H. The prediction is not different. But you see that the vectors underneath, the actual output of the neural network is really different between these two cases. This is a much stronger prediction. And this strength, so the degree to which one of the units clearly dominates in the prediction, I can use as a scalar that in fact defines something that I call reliability index. So I can simply from that difference compile something that I call reliability, and what this curve shows you is that this reliability overall correlates with accuracy on the level of proteins. Since that is the case, in fact, if many of my predictions are down here, I will suspect that the protein for which I predict, although I don't know the answer for that one, but I will suspect that this is on that side. In terms of a probability sense, you see this is not a clear correlation, but there is a correlation. And I can use that correlation to in fact look up if the average is very low, then most likely you sit here. If the average is very high, you're most likely to sit here. Without knowing anything about that protein, just from the prediction itself. That above here is the fit for the per protein level. Here's the fit for the per residue level. What I show, percentage of residues predicted over per residue accuracy, and the curve that is important here is this black one. All residues I predict at 70-something, 72%. That's the average I showed you before. Right? If I only looked at, for instance, those half of the residues predicted with the highest reliability index, then you see that for those, prediction accuracy, somewhere here, is about almost 90%. The actual half is here, 86 or 87%. So without knowing the answer, on a per residue level, you can clearly identify where your prediction is most likely to be right and wrong. And ultimately, this is the most important in some sense. So we now have a tool that can predict much better than anything else. It has those segments right. It has, in fact, a better prediction of beta strand. But ultimately, one of the most important aspects here, it can predict where it's wrong. And that component is something, so when you develop machine learning devices, think about that. That, again, I showed you my grid picture. Maybe that's the point where I should present it again. C'est pas un pipe. So think about, there's always something wrong in your answer. If you can identify where that is tremendously valuable. One particular case, let's skip that. Now here I have an example. I completely timed the lecture wrong today. Can that system predict changes where people, in fact, through engineering, change the structure? And here's such a case that was published, is the Chameleon, published by Kim a while ago. This particular peptide here, So that's a particular sequence. If you throw that into a solvent, as a peptide, not as a protein, just this short stretch, and you do an NMR on it, you see there's a helix. Something that is very, very similar is occurring in this protein here in a helix. What Kim et al. Observed is that something, in fact, very similar is over here, and it's in a beta strand. So that got them to the idea, let's find something that is sort of in between these two. This peptide up here, put it here, and put it here. If I put it into this position, it adopts a helix. If I put it into that position, it adopts a beta strand. Now we have an 11-mer. So we have 11 identical residues. And that, again, is an engineered case. In those days, we had nothing like that in nature. Today, actually, we found cases like that. By now, the database is big enough to have found cases like that. You may remember that I talked about the pentapeptides from Sander and Kapsch in the beginning, when they first developed DSSP, they saw that 5-mers are sometimes in beta and sometimes in alpha. This is an 11-mer, shown engineered to be in one position in the alpha and one in the beta. The method underneath here is in fact the prediction. And in this particular case, it's correctly predicted if you use alignments. So no means the single sequence-based prediction, and the single sequence-based prediction actually gets it wrong. Because that, again, although it sort of had seen something else, sees environments, it's not enough. It's still too similar, and it calls that a helix. You need the alignment information before you really see both trends. So in some sense, you can also predict changes, and the tool has been used again and again for protein design to in fact design peptides like that. Again, 2 courses in the winter semester done by Guy Yagda, JavaScript technology, patterns and anti-patterns, how to better code. Write an email to a Guy if you want to be part of it. We have a limited number of slots. Quickly, I presented that last week, the proper comparison of methods. So I have method A that predicts 60%, method B that predicts 63%. Is B better? That's the question I asked. So the first question that you have to always ask, is it the same measure? By no means you will find in all papers this simple consideration to be considered. So for instance, are both measuring the Q3? Next one. Do they use the same data? Even if they use the same data, and for instance, they both used 100 proteins, and they both said that they, in fact, randomly split. All of that may be in the method section, but it still does not imply that the actual number really is compiled on exactly the same proteins. Instead, what they have to do is really, they used to absolutely need to use the same data set, and they need to use all the data that they have. Split training and testing in random, is that okay? Well, because of a couple of reasons it's not. First of all, you have to ascertain that the similarity between train and test set is such that there is no overlap that would allow you to apply another method. In this particular case, for instance, what you're competing against is comparative modeling. For 1/3 of the protein, you can predict the 3D structure. For those, you can predict the secondary structure. If training and testing set were sampled from above here, you could trivially predict secondary structures just by lookup. So training and testing set must be underneath here. And that's a criterion that you have to, whatever next task you have, set yourself. Make sure. So 63 minus 60 is 3. Is that significant? And again, the question whether that is significant depends on the underlying data, the distribution. That is the distribution for this case of secondary structure prediction. So is it significant now, 3% improvement? If I had 100 proteins? I give you the distribution. I give you the difference. You're the referee. The author says our method is significantly better. Again, the delta between the my method that I'm trying to publish, you're the reviewer, and the method that is already in the database or in the literature is 63 to 60, 3 percentage points in Q3. Both use the same method, both do the right training split, that problem is solved. But is it significant? That's the distribution. How do I get the answer to yes or no from the distribution? Anybody? Threshold. Yes, that's true, but how do I define what the threshold is? So let me repeat, because you're very soft. He says there's a threshold for statistically significant. You're above, you're statistically significant, you're below, you're not. My question here really is, what is that threshold? You're absolutely right. What's the value? Is 3 above or is 3 below? And how, so one, we could just do crowdsourcing again. Ask your dog or something, or ask your coin, or ask your intuition. But I'd like to really have an idea how I get it out. And it's sort of more, crude is fine. I don't want a full math here, or statistics. Rule of thumb, any idea? Using the data that's on the yeah?
I think it's about, you have to look at the standard deviation, and it's about 5 sigma, and that is okay.
That's an interesting one. So your argument is I have 10% of a sigma, and 5 sigma would be a statistically significant difference. In this particular case, that would turn out to be something like 52%. So the only way to improve our method that is 60% accurate is by having one that is 110. I hope I cannot get through you a method that is 110% accurate. In fact, I met somebody who is happy with me telling him that I have a 110% accurate method. I hope you wouldn't be happy with that. So that it could be true. In fact, it's not true. It's true. 5 sigma is 50 something, but it is true. So you're right on that. And you're also right pointing out that sigma is an important variable here. But it would name it could be true, yes. Yeah, well, I'm certainly not giving you a logical argument here. But I have a different answer. So anybody else can, there are a couple of numbers on the whiteboard, on the slide. The number 3, the number 100, and the number 10. Sigma is 10. There's a rule of thumb that essentially combines the standard error by doing the sigma, and again, you're right in pointing out one sigma may not be the best way of going. Several sigma, you said 5, that is really very conservative. Sigma of 2 or 3 is 99%, is already a big step. You take the sample set, take the square root of it, in this particular case 10. 10 by 10 is roughly 1. Plus minus 1 is roughly the standard error. So for this, roughly 10 plus minus 1, the 3 is absolutely above that error. So given the data here, that is clearly, back to your point about a threshold, the threshold would be 1, and 3 is significantly above 1. So the difference between these two methods is statistically significant. But let's assume method B is 20 years older than A. I'm trying to publish A. Is it still better? So I previously tried to publish B. Now I'm trying to publish A, just for the sake of the argument. So again, B is 63, A is 60, and I'm arguing, well, listen, you know, my method is new, the other one is old. I can tell you, my daughter would clearly have an emotional answer to this. Old is bad for her. You're not as young as my daughter, but you're pretty, from where I look, you're more like my daughter in some sense. So is that your answer? Does that change anything? No, it doesn't, right? Is statistically significant, is not affected by the age of a method, absolutely not. Is there any other test that we could do? Mind you, one method is 20 years older. I come today, is there, if you were to be the referee, what would you make me do? Or is there anything that you could make me do?
You can try some new data set.
Exactly. And that is something that you, whenever possible, should always try to do. You extract your data today. Whatever project you do, even a bachelor thesis takes 3 months. So typically, by the time that you write up your thesis, over 3 months, there is something new out there. You believe that your method does something. Test it on the new things and see whether that is consistent. You had never seen that before. It helps yourself to be more confident. After 20 years, clearly there's a lot that we can do. Okay? That's something that you always should try to do. Cross-validation, how to, I talked about that. So this example that I have training 150, testing 150, number of hidden units is 15, 30, 45 in this example. The Q3 is 62 for 15 hidden units, 64 for 30, 63 for 45. The conclusion in my paper was that my method is 64% accurate here. That's the highest number. And in fact, the best number of hidden units is 30. I told you that for this particular case it's wrong, because this rationale would use the test set to optimize a free parameter. Here, the number of hidden units. And in fact, what we should do is have the cross-training set like this. And in this particular case, then I would in fact pick 30, because it's the highest on the cross-validation, cross-training set. Although, as you see on the test set, that hurts myself. On the test set, it would have been wiser to take that one. But still, this is the right answer, even if that's what you observe. Because that is the most likely answer of these two to survive. It is very, very difficult to publish the method like this and then only publish the number 61, although you worked on it for some time and you got to 62. But try to trust the procedure more than you attempt to get a higher number here. And again, referees will sort of possibly say, okay, 61, if you had 62, take it. Don't fall for it. This is the right procedure. Pick this one, right? Tough one. 2 courses, I said that before. And with that, we are at the end of today. Again, Thursday there is no lecture. Next week, Tuesday there is no lecture, so the next Thursday is the next lecture. And then we will continue on secondary structure prediction, and then we will go on to transmembrane helix prediction. Yes?
Wasn't there a change in the schedule that was sent to us by everyone online about, I think the 6th, 3rd? Well, there's no room or something.
So I made a mistake. Most likely. Is that the one where there is no room? Is that?
I think it was just pushed further.
No. I'm sorry. We had the vote on that, and the vote decided that the majority in the room decided on, rather than having it earlier, drop it. There is actually something. Thank you that you bring that up, and I have still time for questions. But something else that I wanted to bring up today. Oh. No, wait. Lothar, do you remember when when Warschau is going to speak in Helmholtz?
No.
I believe it's this one here. So Ariel Warschau is one of the 3 who won a Nobel Prize last year in chemistry on the development of quantum mechanical, or a mixture of quantum mechanical and classical physics for molecular dynamics. And he will talk at 11 o'clock, I believe, on the 26th in the Helmholtz Center. I can clearly tell you I would like to attend that lecture. If you want to, then that lecture will actually, I will not give my lecture, we will meet at the Helmholtz. So the room I wrote down, but I don't have the paper here. Again, it's the Helmholtz Centrum. I don't know how you get there. Is there public transport from here? Or from Garching or from Munich?
Complicated, you have to take several buses.
Okay, so the good news is public transport gets you there. The bad news is it may be as complicated as getting to Garching at the moment, or maybe even more complicated than getting to the university at the moment. So Who is for skipping the lecture with the objective of going to Helmholtz? Ooh, I have to give a lecture. Who is for being here and having a lecture? On the 2, 3, 4, 5, 6, 7, 8, 9. Oh, I wanted to hear Arya Rost. Okay, how often do you get to hear a Nobel? How often have you heard a Nobel Prize winner? Often? So you went to the Nobel Prize Symposium or what, in Lindau?
Lindau, I went to Lindau.
Yeah. That's cheating. So he got one of the 5 slots for one of those. Okay. Thank you. Any question? So there will be a lecture. I'm not entirely sure how I push the program through, but as it stands at the moment, it will be about contact predictions.